Alright, hi everyone. Nice to see you guys again. We're going to go on to the next section of the book, which is section 4.2, the definite integral. So, as promised, we're going to talk about this thing called the integral. And we basically have been dealing with this. We just haven't called it the integral, but like I said, sooner or later we would call it that. So, what do I mean by the integral? Remember, we were talking about the area underneath the curve. And this was the formal way of getting the area underneath the curve. Remember, we had a sub n, which was the area that we generated with n rectangles. And this was equal to, remember, we used the different sample points. So this was the height of like the first rectangle, and then this was the base, and then the height of the second rectangle times the base again, and so on and so on. There's like a small technical point where if we make this n minus 1, that would work here. So let me make this 1 and make this n just so it's a little less confusing. Okay. And so this would have to be a 2. Okay. So this is just saying this is the first rectangle's area, second rectangle's area, and so on. And then, like we said, you can just always factor out this delta x to get just this guy here. And then if we used our fancy sigma notation, we can write this even more compactly as this whole sum, remember, is this number delta x times this sum from I equals 1 to n of this guy. Okay, so this was the area. And then we said the limit as n goes to infinity of the area, which is the same as this, we define this to be the area underneath the curve. So this literally is when you take an infinite amount of rectangles, you get the area underneath the curve. Okay. Now, we're going to introduce some terminology here. And so we're going to say that, if this sum makes sense. Because in some cases, this doesn't make sense, but for the purposes of this class, more often than not, it will make sense. But whenever this sum makes sense, this is what we say. And now we define it like this. So now here's where the new notation comes. So instead of writing this, we're going to write okay? And I'll tell you how we read this in a second. This literally equals this. Okay. So we read this as, this is how you read this, the integral, so in quotes, the integral of f of x from a to b. Okay? And remember what a and b had to do in our context of what we were doing. So we had, we had our function, had some function here, and then this was a, and this was b, and we wanted to calculate the area underneath the curve. So from A to B, we wanted to calculate this area. This area right here is exactly what this is equal to. So this area is equal to this thing here. So that's what this collection of symbols just means. Yeah, this is just the area from A to B underneath the graph of our function. So this thing here is called the definite integral. We'll run into something called the indefinite integral a little later. You've basically already done it, but we haven't used the fancy words for it. So this is the definite integral. Definite. Because it gives you a definite answer for the area. It gives you one complete answer. And a little bit of other notation that we say. Maybe we can erase some of this to clear this up. Okay, so this thing here is the definite integral. The sums here, basically the sums of the rectangles that we were talking about, when you add up the area of these rectangles that you get when you make different, when you use different sample points and different number of rectangles, whatever, these are called Riemann sums. So this sum here is called a Riemann sum. I'm hopefully spelled that right. Yes. I don't know if it was one N or two N, but yes, this is after a very famous German mathematician, Riemann. So the sums of the rectangles, they're called Riemann sums. Okay, so the stuff we were doing in the last section where we were calculating the area by adding up the area of each of the rectangles, those are Riemann sums. We just didn't say that. Okay? And then we also need to introduce this concept that, again, has a parallel to derivatives. So remember, not every function we could take the derivative of, right? Remember, like, for example, the absolute value of x. At 0, this point is non-differentiable. So f prime of 0 didn't exist. It had no value that we could assign it to. And similarly, so we said that a function is differentiable if you could take its derivative at some point. Or it's differentiable on an interval if you can take the derivative on every point in the interval. So we have an analogous concept of integrable. So a function f of x is integrable on an interval a to b if, so basically you can find the area underneath the curve of this function from a to b. That's what it means to be integrable. So it basically means this Riemann sum, this limit as n goes to infinity, exists basically. If this thing exists. Okay? So if this limit exists, then this thing makes sense and we just write it with this symbol. And that is the value of the definite integral. So just like we have differentiable, we also have integrable. Okay? Now, it's a lot easier for a function to be integrable than it is to be differentiable. And we can see that right here because this little thing that we're going to talk about right now is basically very useful for our class because we know what a continuous function is. So this is a theorem here. So if f of x is continuous on a to b, so remember continuity from Calc 1 way back when. If not, definitely can brush up and ask me questions on this. So if a function is continuous on an interval, then it is automatically integrable as well. So just like that, continuous implies integrability, but the opposite with differentiability was not true. Remember, if a function was continuous, it did not have to be differentiable. As we saw with the example with the absolute value of x, that function is continuous, but it wasn't differentiable at 0. So it's easier to be integrable in a sense. And actually, you can actually relax this condition a little more too. So even functions that are not continuous, if they're not too badly discontinuous, they can also be integrable as well. And what do I mean by this? So as long as the function is not too crazy, you can still find the area underneath the curve. So this is another theorem. Okay, so we're going to consider a function that just has a finite number of jump discontinuities. Remember, these were discontinuities where the function kind of jumped from one value to the other. So let's say it was -1, and then it suddenly jumps to +1. So this was like a jump discontinuity. So as long as you only have a finite amount of these, the function is still integrable actually. Okay, so these two right here, conditions here, basically make most of the functions that we have seen in this class and will see integrable. So the question of whether something is integrable or not is pretty often yes. We're most likely, yeah, you can find the area underneath the curve, which is good. We don't have to go running around doing all this fact checking. Okay, so now that all this stuff has been established, we have a little bit more notation to do. So like we said, if you can find the area underneath the curve, so if that Riemann sum exists when you let the number of rectangles get very, very large, this thing makes sense. This has some value. So A and B are called the limits of integration. So A and B are limits of integration, and then B is called the upper limit. So this is the upper limit, and A is called the lower limit. And then the thing that you're taking the integral of, the function whose area underneath the curve you're finding, is called the integrand. So f of x is called the integrand. Okay, so this guy right here, that's the integrand. Okay, And you may be wondering, what the heck is this dx business here? You could think of dx as delta x, but where delta x gets really, really, really small. Because if you think about it, what was delta x? Delta x was b minus a over n being the number of rectangles. The larger and larger you make n, the smaller this quantity becomes, because b minus a is a fixed number. So let's say it's like 3. Well, 3 divided by 100 versus 3 divided by 10 million, right? When you divide it by 10 million, it becomes much smaller. And then let's say you divide it by 10 trillion, it becomes even smaller and smaller. So as n gets very, 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 very large, delta x becomes this very small increment, like an infinitesimally small width. And that's what dx kind of represents. It's trying to capture that. And f of x is like what we saw is like the sample points, the heights here. So f of x is kind of like the height at the sample point, and this is like delta x. So this kind of becomes a like continuous version of what we were doing, because the sum was discrete. We were adding just like a finite number of points together. Area 1, area 2, area 3. Here it's saying get really, really, really small areas and just add those really infinitely small areas all up together. And that gives you the exact answer. So intuitively that picture makes sense, which is good. Okay. So now that we've defined what the definite integral is, we can maybe see an example now, which again won't be too different because in the last section we were finding definite integrals, we just didn't say that. But we never mentioned the case of what happens when we have like a function that goes underneath the x-axis. So maybe it has negative values. So maybe the function looks like this. So if this is a and this is b, how do we deal with that? So here's a and here's b. So this area here, these are like positive areas. They contribute positively to the area. But then the area down here that we get like that, that's going to contribute a negative area. So, we say area underneath the curve. It doesn't really make sense here, right? Because this is like the area above the curve. So underneath the curve was in the context of where, the function has positive values. So it's under it, but in the case of it has negative values, it's like above it. But, it's kind of just semantics at that point. But what would this integral be? So if this is our function f of x, the area, aka the definite integral, so the area underneath the curve, which symbolically is this would be equal to, let's say the positive area is a1. And then a2 is the negative area. We're going to count this as negative, which calling it area is weird, but it's just the idea. So a2 is negative, so not surprisingly, you're just going to take this a1 and subtract it from a2, if we think about it as negative. So, or you could add them, right? If you take a positive number and you add it to a negative number, it's kind of just like subtracting. So this is going to be a1 minus a2. So a good observation from that is this. It does not have to always be positive. The area underneath the curve, we say, doesn't really always have to be positive. This thing can be negative. It can also be 0. So it's fine, negative or 0, let's say. So it doesn't just have to be positive all the time. That's kind of like the key point. And so let's do an example here where we deal with this. Let's see how we can kind of think about these positive, negative areas. Okay. Okay, so let's say we take the function f of x is x cubed minus 6x on this interval 0 to 3 with six rectangles. So that means n equals 6. Okay, and we can't find the exact value of the integral. Remember, because that's just going to require a little bit more. That's in the future. Right now, we're just going to approximate it and be happy with that. So for now, we'll just approximate it and be good with that. So the question is, what kind of sampling should we use? Should we use left endpoint, right endpoint, whatever? The book uses right endpoints in this example, so for the sake of helping you guys follow along, we'll do right endpoints. So we'll use right endpoints. Okay, so what does that mean? So remember, the trick was you're going to find delta x first, which was b minus a, so 3 minus 0 over n, 6. So we know that the width of each rectangle is a half in this case. And then remember, this gave us a bunch of subintervals. So in this case, since n is 6, we're going to get 6 subintervals. So the subintervals that we have are the following. We have 0 to, okay, because we start at 0. But if the width is a half, we're going to go from 0 to 0 plus 1/2, aka just 1/2, right? So that's the first subinterval. Then the second one is, well, you start at 1/2 again, and then again you add delta x, so you get to 1. So 1/2 plus 1/2 gives you 1. And then if you repeat this, we get 1 to 1.5, and then 1.5 to 2, 2 to 2.5, and then 2.5 to 3. Okay, so we get these 6 subintervals. And then with the right endpoints, what we're using is basically the larger number in each of these. So the sample points will be these. So this is just, we'll just keep track of this. So sample points in this case will be 1/2, or maybe I'll number them too. So x1, the first one will be 1/2. x2 will be 1. x3 will be 1.5. x4 will be 2. x5 is 2.5, and x6 is 3. So these are our sample points, these 6 points, because we took the right endpoint. So we're taking the larger number essentially in these subintervals, okay? And then of course we want to graph this guy to see what the heck is going on. Normally at this point you really don't have to graph anymore, because you have your sample points, you have your delta x, and you could just put this into the Riemann sum formula. But for good measure, let's kind of graph what this looks like, just so you can see, because this does have negative areas actually. So we're going from 0 to 3, and then these are our sample points, so 1/2, but yeah, so 1/2, 1, 1.5, 2, 2.5, and 3. Okay, And then remember the function was x cubed minus 6x. So, you know, to figure out what the curve looks like, you can just plug in some points, right? So what happens when you stick 0 into the sky? Well, you get 0 cubed minus 6 times 0, which is 0. So this is 0. And then what happens when you stick 1/2 into the function? So if you do this, you get negative 2.875. All right, because it's going to be some fraction, so it's fine. Okay, so negative 2.875, that's the value at 1/2. And then what's the value at 1? Well, it's going to be 1 minus 6, so this drops down to negative 5. And then what's the value at 1.5? It's negative 5.625. Okay, so slightly less. And then what's the value at 2? Well, 2 cubed is 8, minus 6 times 2, which is 12, so 8 minus 12, so it jumps back up to negative 4, which is like somewhere here. And then what's the value at 2.5? It's 0.625, so now we're back to positive. So at 2.5, positive, and then at 3, it's 3 cubed, which is 27, minus 6 times 3, which is 18. So 27 minus 18, so that's going to be 9. So we jump all the way up here to 9. Okay, and so, you know, we can make a list of, remember these are the sample points, but we have corresponding outputs for them now too, right? So we know, for example, like f of x1, right? Normally we would have a star here, but star meant an arbitrary sample point. We're using the right endpoint, so we don't need the star anymore. We know what it means. So f of x1, aka the height of the thing, is going to be negative 2.875. F of x2 is, this is x2, right, is negative 5, and so on. So we have a list of the heights as well. So we're very prepared to calculate the Riemann sum, is what I'm saying, basically. And so let me maybe fill this curve in now. Oops, missed the point. Okay, so maybe the curve looks something like this. Okay, again, my drawing skills are not the best, so you just have to bear with me. And so again, this is the same idea, is the width of the rectangle is 1/2, but the height we're going to use is exactly the f of x1. So the height of the rectangle that we're going to use is this. So width of 1/2, height of that. So this is the area that we're getting right here. So that's one rectangle. And then f of x2 is negative 5. So again, we have a width of 1/2, but the height we're using is negative 5. So this comes down here because the width is 1/2, and the height caps off at negative 5. So you can see that we're getting some negative areas. And then again, we're getting quite a bit of negative area, I guess, not just some. Oh, sorry, I messed that one up. So the height only goes up to this point now, right? Because the value at 2 was negative 4, so we cap this off at negative 4. So see, we're missing this little area here. So the width is 1/2, and the height is negative 4. And then last but not least, we have the other ones. So at 2.5, we're up here. So we get this small area, and then at 3, we're up here. So we get that. Okay. All right. So yeah, that's roughly. So the Riemann sum that we're talking about is basically just the sum of these 6, the area of these 6 rectangles, where area, I mean, can be negative. So these will be negative areas, these will be positive ones. So when we calculate the Riemann sum, so the integral from 0 to 3, because those are the boundary points that we use, 0 to 3, of f of x, which f of x in this case is x cubed minus 6x dx. This is approximately, not exactly, because we haven't used the infinite amount of rectangles, it's approximately going to be the sum of these areas, which again, remember, you can just pull out the delta x. So delta x was 1/2. And then you multiplied it by what happens when you stick these sample points into the function. So it's going to be, I'll put the, maybe, so yeah, it's going to be negative 2.875, and then minus 5, and then I'm running out of space, I probably need to not close this bracket off here, minus 5, minus 5.625. So what happens when you stick this into your function, and minus, oh, maybe I'll write this here, or how about I just erase this, since we kind of already have that picture. Spacing problems. Sorry about this. So let me reiterate. So this guy, the area under the curve. So you read this as the integral from 0 to 3 of x cubed minus 6x is, this guy was approximately going to be 1/2 times negative 2.875 minus 5 minus 6.625, sorry, 5.625 minus 4 plus 0.625 and then last but not least plus 9. Okay, so this is just each of these is the output of the sample points. So the height, how low or how high you went. Okay, and then when the dust clears and everything happens, this is approximately going to be then negative 3.94. So see, we do get a negative value for this, so that's fine. That's perfectly fine. So the area underneath the curve, which with all these fancy symbols is like that, is approximately negative 3.94. Again, it's not perfect because we didn't use an infinite amount of rectangles, but we'll talk about how to get the perfect answer. And I've kind of already told you, but I won't spill the beans too much. Okay. Now, for certain scenarios, we can actually get the area underneath the curve basically perfectly. And so what do I mean by that? Say the function that we get ends up giving us some geometrical shape whose area we already know. Okay, so remember, what was the equation for a circle? So a circle of radius r had this equation. X squared plus y squared equals r squared. And what does that mean? That means that, you know, the circle has radius r, so that's r, and that's negative r, that's r, that's negative r. And I take some random point, right? This is just some point x comma y in the coordinate plane, right? It's just some arbitrary point x, y. If I square this number and I square this number and I add them together, that should always give me the square of the radius. That's what it literally means to be on a circle of radius r. It means that, you know, this point is not on the circle. So if I square the x and y coordinates, I won't get r. Like for example, the origin. This is 0, 0. 0 squared plus 0 squared is definitely not r squared. So only the points on the circle will satisfy this. Okay, and that's why that's the equation. So that's what x and y refer to. So if we do a little bit of algebra and subtract x squared from both sides, then we get that y squared is r squared minus x squared. And then if we take the square root, we get two different scenarios. We get either you have the square root of r squared minus x squared, that's y, or you take negative, right? That's going to be the lower and upper branch. So, right, when you take the square root, you get plus or minus. Maybe I should write this for emphasis, and maybe I'll even make this a different color. So one square root gives you the plus, the other square root gives you the minus. So plus or minus. And so what happens is this guy is the equation for the top half of a circle. So in the coordinate plane, this is going to give you the top half of the circle. This is r again, that's negative r. And then this one will give you the lower half of the circle. It doesn't look like the best circle, but it'll do. Okay, so these are very nice formulas because we know that we're dealing with a circle if we ever see them. So let's now maybe see what we can do if somebody asks us to find this now. So let's say somebody asks us to find this guy. You're going to be like, oh wait, I know exactly what this is. This is like the radius in this case, right? Like 1 squared is still 1. So we have r squared minus x squared. So this is a circle of radius 1. So in this case, our radius is 1. AKA we have the unit circle, if you remember from trig. We have the unit circle. And we're taking the integral to be from a equals 0, so from this point, so a equals 0 is that point, to this point, b equals 1. So we're finding essentially the area under the top half, right? Because we're taking this area here. We're finding the area from 0 to 1 of the top half of our circle, which is going to be 1 in this case because our radius is 1. Now you may ask, well, why aren't you taking this half either? Well, they're not the same function, right? 1 minus x squared is just the top branch. Negative square root of 1 minus x squared is the bottom branch. So we're just literally only looking at this case. And from 0 to 1, that's just this guy right here. Okay? And so this, well, I mean, now we can basically use, like I said, formulas from geometry that we already know to give an exact answer. No Riemann sums or anything needed. No weird limits or anything. So what is the area of a circle normally is pi r squared, right? The whole thing is pi r squared. But how much of a circle do we have is a fourth of a circle. So we have 1/4 times pi times our radius is 1. So this is just going to be pi over 4. So that's the exact answer. So this thing has area pi over 4. Very nice. And right, this looks so intimidating, but if you know what the picture represents, it's like very straightforward math that you've seen for a long, long time. Now, what if somebody asks you to find this guy? Okay, so now this is our function. The function is x minus 1. Okay, now, of course, let's plot this. Let's see what this means. And, you know, depending on how much college algebra, I guess you remember, you'll recognize that this is just the equation of a line, right? This is a line with slope 1 and y-intercept -1. Because, right, the m here, the missing m, the slope is 1. That's like m. mx plus b, well, b in this case is negative, so this is like b is -1. So yeah, this is just a line with slope 1 and y-intercept -1. But again, you could just plug in points to see what this is. So if you have f of x is x minus 1, we're just going from 0 to 1. So what happens when you stick 0 in here? You get -1. So that's the point. And then what happens when you stick 1 into this? 1 minus 1, you get 0. So let's put this maybe all the way over here. So that's what this guy looks like. It's just a straight line. And so the area that we're interested in finding is this one right here. Well, I mean, do we even need rectangles anymore at this point? Because this is the area of a triangle. We know how to find the area of a triangle very well. So in this case, again, this really weird looking, daunting looking integral is not too bad actually. It's just going to be, so remember, what's the area of a triangle is 1/2 times the base times the height. So this is going to be 1/2 times what's the base length, which is 1, times the height here is not necessarily positive, it's -1. So this is going to be -1/2. So again, this really daunting looking symbols, all this mumbo jumbo, all it's saying is find this area, which we know is -1/2. Okay, so not too bad. Okay, and then, so that's something good to notice, is that if you can draw a picture out of this, you don't need to resort to these weird Riemann somethings. But if you get some curves, you know, and it's not like a circle or something, if you have any kind of curve in your graph, we need to use the Riemann sums, because you're not going to have a straight line like this. If you have a straight line, perfect. That's excellent. Okay, and then now let's get to some of the properties of the definite integral. So remember, like with the derivative, we had a lot of properties, right? Like if you, for example, if you take the derivative of two functions, when you add them together, that was the same thing as just taking the derivative of each function separately and then adding them. You know, the sum rule or the product rule is, or you know, we had all of these rules and properties and things like that about the derivative. We want to establish similar results, but with the definite integral now. So the first one that's up is going to be this. So maybe I'll just say property 1. doesn't have a name, is this guy. Okay, so the big thing to look out for in this is that the minus sign is here, and notice what happened there. So in a nutshell, what this means is if you want to flip the limits of integration, the order that you're integrating, you have to pick up a minus sign. So that's all that this is saying, is you'll pick up a minus sign in doing so. Which this property comes very handy in a lot of scenarios, and we'll see. So then the second property, and like, you know, we could sit here and prove all of these, but I think for a first run of calculus, this is definitely good enough to just see these just displayed and how they're used. So then the second property is, how do they write this here? Yes. Zero. Property 2, sorry. Notice these limits of integration are the same. That's the key here. Same limits of integration. So, I mean, this also intuitively makes sense, right? If you have a function and you start at A and you end at A, you're finding the area just underneath this one point. Well, how much width does this thing have? It has no width, right? So it can't possibly have any area. So that's why it's 0. So if you don't go anywhere from A, if you don't have a B to go to, then, I mean, right, there is no area. And this is the area, essentially. So this is going to be 0. Which, again, is, these are all very useful properties that we'll see used over and over again. Let me rewrite this. So yeah, if you don't go anywhere, of course, you're not going to pick up any area. And then next up, we have this one. Is so if you're finding the area underneath a curve that's just a constant horizontal line, then the area is just going to be C times B minus A, which this one, I guess, we can prove because it doesn't require too much complexity. It's pretty straightforward. Because if you think about it, if you have the function y equals constant, or y equals C, for example, y equals 2, all that is a horizontal line, C units if it's positive, up or down if it's negative. So this is y equals C. And let's say that this is A and this is B. So the area underneath the curve of this thing is just this guy here. Is this rectangle, is the area of this rectangle. Well, what is the base of this rectangle? The base is B minus A, right? The length of the base is B minus A. And what is the height? It's C. So base times height. So the area underneath the curve is just the base times height. So this is pretty quick to see. And then maybe I'll just erase this and start new. And then, let's say, I think it's property 4 is this. Okay, so this is going to be exactly the same as with derivatives. So if you're adding or subtracting two functions and you want the integral of that, you can just take the integral of each one separately. So you just take the integral so find the area under the curve of each function separately and then add or subtract them. Or you just do it in one go. So this says you just do it all in one go. This allows you to break it up into two different pieces and then add or subtract them. So we'll see examples of this here in a second. This is very useful. And then last but not least, or maybe there's some more, we'll see. Again, so if you have a constant and you multiply it by your function, this is again something that similarly happened with the derivative. C times f of x. This is the same thing as just finding the area underneath the curve and then multiplying it by your constant c. Okay, and maybe let me give you a nice geometric picture for that one. Okay, so let's think about the function sine x from 0 to pi. So it looks roughly like this. Let me scale it well. Okay. So this is sine x. Oops. So this is sine x. Okay. Now, what happens if so f of x is like sine x. Now what if we take c to be 2? So we have 2 times sine x. So remember the peak here normally was at 1 for sine. Now if you do 2 sine, the peak jumps up to 2. So this is 2 times sine x. So c is like 2 in this case. Now, whatever the area underneath the curve is here, this thing right here, this area right here, this is the area under the curve. We write it like this. How does the area of this guy compare to the one that we have, 2 times sine x? Okay, well, it looks like twice as high, right? So you would literally just double this guy. That's all it's saying. If you take this guy and double it, so this is really just 2 times the old area. Sorry, this should be 0 to pi. And that makes perfect sense, right? Because the area now, the hole under the red one, it is going to be twice this area that we originally had. So that's all that this rule is saying. Instead of worrying about the constant, you just find the area under the base function f of x and then just multiply to stretch it out, because the c stretches it or shrinks it. This will just take that into account. So again, this rule extremely important, and we'll see examples of it here in a second. Okay, so now let's see examples of all of this. Okay, so let's see some examples. So let's say we want to find this guy. So the area underneath the curve from 0 to 1 of this function. Okay. Now, one of the properties will allow us to split this into two different integrals. So that was the property that allowed us to split things. So this is going to be the same as, right, that's like one function. So f of x was how we wrote it, and this was like g of x. So this is like, in the way that was written in the property, that's like f of x, and this function is like g of x. So now you have the integral of f of x plus the integral of g of x. Had this been a minus, this would be a minus. Okay, so that's one use of the properties. Now, another use of the property is, right, this is a constant. So what did we say the area underneath the constant was? I mean, if you picture what this looks like, this is just a horizontal line 4 units up. And here's 0 and 1. It never changes. So what's the area underneath this guy? Well, it's this length, which is 1, times this height, which is 4. And that's all that formula was saying. Is C, this is like C in the property. And this is B. And this is A. It said it's C times B minus A. So it's 4 times 1 minus 0, which is exactly what this picture is telling us. The base is 1 minus 0, which is 1, times the height of 4. That's what the area is. Okay? Plus now again with the other property, the last one that we did, it says that this 3 here, you can pull it out and multiply it later. So we're just going to look at what the integral of x squared is. So this, you can pull out this 3 and just look at this instead, which is really nice because we've already worked out this number. It was 1/3. We didn't know it for 3x squared, so we would have to redo all of this stuff in a sense to figure it out. But this nice property just says, oh, it's okay. Just find the area underneath this original function x squared and then triple it. That's it. So this becomes, what, 4 plus 3 times, and we talked about in the last section that this is 1/3. So 3 times 1/3. So this is just 4 plus 1, so 5. So that's the answer. So let's summarize. So the area underneath the curve of this function, right, we don't even have to know what it looks like anymore. We don't have to graph this and do the Riemann sums in this case. It's 5. So yeah, that's a really nice combination of all of those properties that we saw. Okay, next we have more properties, of course. Never ends. So I believe we left off with 6, so this will be property 7. Is this. Okay, so let's see if we can make geometrical sense out of this. So notice, this is from A to B. This is from A to C, and this is from C to B. So all that this is saying, say you have your function, and then here's A, here's B, And then here's like some random point C between them, right? Now, if you take the area from A to C, so this right here, so the area from A to C is that. If you take that and you add it to the area from C to B, right? So A to C, that's why this is A to C. C to B, that's why that's C to B. If you add these two areas up, it's just the area from A to B. It's the whole area. So the area from all the way from A to B, basically the sum of the blue and red, is just the sum of the individual pieces. That is all that's saying. Which again is, this is going to be used a lot. It's very useful property. Okay, which, let's see a nice example of this now. And this will kind of use that theorem about the jump discontinuities that we saw earlier. So we're going to consider this function, very famous function. So let's think about this function. So what does it look like? So it says that you have a value of -1 for negative numbers. So here's -1. And it's constant, right? It's always -1. So no matter what my input is, the output is always -1 for negative ones here. And then magically when I get to 0, so I need to put a hole here. I should clear that. When I get to 0, I jump up to 1. So then I fill this in, I go that way, and here's 1. Okay? So this is what the function looks like in general. And notice this is a jump discontinuity. But we can actually figure out the area underneath the curve here. It's pretty neat. So this function is still integrable. Even though there's a big jump in it, we can still find out the area under the curve. Which geometrically makes sense, right? There's no reason why we can't do this. So, and we're going to use this property to help us out to figure out this. Let's say we want the integral from -2 to 5 of our function here, f of x dx. Okay? Well, the thing is, this function has two different, expressions depending on where we're at. So what we're going to do is we're going to break this up into two pieces. One piece is going to be from -2 to 0. So let's say this is -2, meaning that we're going to find this area. And then let's say that this is +5. So there's this area. So this guy here is asking, if you add these two areas up, what do you get? That's basically what the answer is. So from -2 to 0, right, C in this case is like 0. It's kind of the intermediate point. From -2 to 0, the function has a value of -1, so it's literally just -1 dx. And then we can pick off from 0, so from 0 now to 5, it has the value of 1. So see, that's how we're using this property. We're breaking up the integral into different pieces, which is really, really helpful. Okay? sorry for all the jumble. This is about the biggest board I have, so this just has to make do. So let's reiterate. This is going to be this is 1. Okay, and so now this is not bad. What's this red area? This guy is the red one. So this one is, maybe I'll write it in red. What's this width is -2, or you can just say 2. And then this is 1, right? So this is 2 times 1. So 2, but it's a -2. So this is going to be, and then again, if we use that property, it's C, which is C is -1, times B minus A. So 0 minus -2. And then plus, again, if we use that property, this is 1, C is 1 in this case, times B, which is 5 minus A. Right, and again, this width is 5, the height is 1, so the area is 5 times 1. So when all of this clears, what do we get? We get, this is a positive 2, so times -1 is -2 plus 5. This is 5. So we get a net answer of 3. So that's how that property is being used. So this area here has a net area of 3. So there's a lot more positive than negative, which makes sense because we went to 5 here and just to -2 there. So that's how that very important property gets used. Okay, so that'll be it for this lecture. We'll wrap up the rest of the properties of the definite integral and move on to the fundamental theorem of calculus next time.